Today's topic is artificial neural networks. Have you ever wondered how they are built and what mechanisms drive this algorithm? Today, we'll dive into these questions and implement such a network from scratch in Python without relying on any high-level frameworks that often allows us to avoid digging into underlying details. You'll see how layers work, what an activation function is, how backpropagation functions, how batches are handled, and how all these elements come together to form a neural network. Let's get started. Artificial neural networks are mathematical models inspired by workings of biological neurons, capable of adapting and learning from experience. Although the origins of neural network date back to the mid-20th century, they only gained widespread popularity with increased research and computational power. Now, they seem to be present in nearly every product we use. The reason for this is their potential to build and train powerful machine learning algorithms with a vast range of application. Neural networks can be used in supervised and unsupervised learning, predicting various business indicators, recognizing images, generating visual and text-based content, and more recently, powering large language models like ChatGPT. Despite their complexity and diversity, at the core of all these models lies the same concept, a neural network composed of few key elements. Let's take a closer look. As you may already know, neural networks are commonly represented as a web of connected nodes organized into layers. This type of model has three fundamental components: inputs, where we input the information we have; layers of interconnected nodes or artificial neurons; and outputs that provide a result or answer to the posted question or problem. In this structure, information flows from one end to the other, that is, from the inputs to the outputs. This is often visualized in diagrams as a flow of information from left to right or top to bottom. Here, it's worth explaining two popular terms. Hidden layers. These are intermediate layers that are not directly connected to the network's input or output. Deep neural networks. These are networks with more than one hidden layer or network with a higher number of such layers. This is where the term deep learning comes in. The fundamental building block of a network is the neuron, which consists of few critical components involved in processing input information. Here is how this process works. A neuron receives a set of information X as an input. This data is a set of numbers describing a particular observation related to the problem we want to solve. Each input value X is multiplied by corresponding weight from the weight set W. This weight set is initialized with random values but will be modified during the learning process. Then, the product of the input and weight are summed together, and the bias term B is added. Like weights W, this term will be adjusted during the training. Both W and B serve as parameters that store the knowledge acquired by neuron. The result of this summation is passed as an argument to the certain function, which can take different forms depending on the choice and the needs of the network's designer. We call this function the activation function. The value it returns is passed as an input to the next layer's neurons, or, if it's the last neuron, treated as a network's output or prediction. Let's pause for a moment to discuss the activation function. As mentioned, it can take various forms. The slide here shows only a few examples from a much broader list. They differ in their characteristics, particularly in the range of values they output from the neuron. Depending on the problem type and the nature of the predicted value, different activation function might be most suitable. For instance, if you are trying to predict the probability of an event, the logistic function is a good choice. Looking closely at the computation within a single neuron, we can write a formula for a neuron's output value. Y equals the output of the activation function applied to the dot product of the weight vector w and input data vector x plus the bias term b. This is how it looks when we work purely with the concept of traditional vector like a series of coordinates in space. The notation of this operation looks somewhat different when we have more neurons in the layer and across the network. In this case, we use matrix notation. We can still represent input vector x as a matrix with a single row. However, we can record the weight vectors for all neurons in a layer within a table. This organization of data is convenient because it allows us to continuously represent mathematical operation not only within a single layer, but for entire network as well, where the output of the layer becomes the input of the next. In this scenario, the dot product, which yields a single number, is replaced by matrix multiplication, resulting in another matrix. I found a great animation on geogebra.org that presents the process of matrix multiplication step by step. This operation might seem less intuitive at a first glance, but it enables us to obtain a full vector, or if you prefer, a matrix of result, not only for a single neuron, but for an entire layer. Matrix multiplication comes with a few extra things to keep in mind. For example, matrix multiplication is not commutative. The number of columns in the left matrix must match the number of rows in the right matrix. Additionally, the shape of the result is determined by the number of rows in the left matrix and the number of columns in the right matrix. Let's continue now, keeping in mind that the product of two matrices is another matrix. Due to certain matrix properties, the letter T appears in our formula. This denotes transposition, which is necessary to meet the dimension requirements of multiplied matrices and the resulting output. Transposition rearranges the elements of a matrix, turning its rows into columns, and vice versa. Armed with an understanding of how outputs are calculated for each layer in neural network, we can see a clear flow of information from input through each successive layer to the network's final output. The resulting matrices from one layer become the input for the next layer. This process is called forward propagation. Let's return to the example of single neuron where the output represents the entire network's output. The network's purpose is to evaluate future input data and deduce solution for the posed problem. In supervised machine learning, we often have a set of historical data where along with the inputs, we also know the actual solution to the problem. During training, the network makes prediction on this data, producing results that can then be compared to the real values we observed when collecting this data. The difference between these two values, or prediction error, will be initially quite large. In fact, it will be random because of the initial random weights W. Our goal is to adjust these weights and the bias term B so that this error is minimized, ideally approaching zero. So the essential question is how we can change W and B to minimize the error. The solution is to introduce adjustments to these parameters during prediction on data where we know the correct answers. The adjustments should be calculated to increase the accuracy of future prediction. To achieve this, we use a process called backpropagation. I'll skip the full mathematical derivation here, but in essence, this algorithm is based on minimizing a cost function defined as the mean square error. In this video, I'm aimed to provide more intuitive understanding of how it works. Let's go through the steps one by one. As we know, a neuron calculates its output based on a certain value that we will call z. Recall that it's a sum of the products of inputs and their corresponding weights plus the bias term. To obtain the prediction value from a neuron, We simply pass z into activation function. The key value we now introduce is the delta error. This isn't the same as the prediction error we saw earlier, rather it's the error encountered when minimizing the mean square error cost function. Delta is proportional to the difference between the predicted and actual values and the derivative of the activation function for the given z. The error related to the prediction itself is quite intuitive, but the activation function's derivative tell us how quickly and in what direction the value of the origin function changes for a given z, meaning for a given set of weights and bias term. Delta error is important because the correction that the network makes during the learning are proportional to it. Once we know the delta error, we can determine the correction we need. These corrections are proportional to delta, with correction to weight w also dependent on the input x that causes this error. Finally, we scale both adjustments using the learning rate LR, which we choose as a network hyperparameter to control how fast the neuron learns. When setting LR, we have to balance the learning speed with the precision of the steps made during training. Ultimately, for a single neuron in the output layer, this process looks as follows. However, a question arises: how do we determine parameter changes for the neurons in hidden layers? For this, we don't have the labels y true as we do for the output layer. Instead, we need a way to calculate delta errors as a partial contribution to the total output error. The difference for hidden layers lies in the formula used to calculate the delta error. It's the sum of all errors from the next layer, weighted by the connection weights between these neurons and the neuron for each we are trying to calculate the error. Like the output layer's delta error, it's also proportional to the derivative of the activation function at the point z of the hidden layer neuron. In other words, the error for this neuron depends on the sum of all errors to which it contributed, with each contribution weighted by the connection weight between this neuron and the neurons in the next layer. So this situation is similar to that of the output neuron. However, to calculate weight adjustment, we need to start with the next layer's adjustments. This led us to calculate this correction for the network's output and backpropagate the determined error through each layer in reverse. This process of propagating the error backwards from the network's output layer towards the input is known as a backpropagation. It's during this process that the network learns and adjusts its weights based on comparing its prediction to the known label or actual value. We are now ready to implement the neural network from scratch in Python. Now, let's get into implementing our artificial neural network. To start, we'll assume a fully connected network structure where all outputs from one layer are connected to all neurons in the next layer. For our implementation, we'll use NumPy library to handle matrix operations, which will involve multidimensional arrays. Let's import this library now. Before diving into the network implementation, let's first create a function to generate the data on which our neural network will train. Each sample will consist of 3 random numbers in the range of 0 to 10. We will then calculate the output for each sample based on a linear equation with coefficients 2, -3, and 0.5. The function will generate n such samples along with their corresponding outputs. For our networks to function, we will need activation function and their derivatives. Activation function operate on NumPy arrays, meaning they takes arrays as argument rather as single value. Out of the many activation functions available, we will implement only 3 and use only 2 of them in this project. The first function is sigmoid. Next, we have the ReLU, rectified linear unit function, which we'll be using in our network. Lastly, We will implement identity function, which we also use in our model. To simplify the code, let's create a helper function getActivation that selects the appropriate function based on the string argument. It will return two objects, the activation function itself and its derivative. Before we build the neural network, let's create its building block, the layer class. In the init method, we initialize several parameters: the number of neurons using the units argument, the number of inputs for each neuron, input size, and the activation function along with its derivative using activation name. The weight and the bias arrays will be initialized with random values and sized according to number of neurons by number of inputs and number of neurons by 1, respectively. Next, let's create forward method which perform computation on the entire layer for multiple samples at once. The np.dot function performs matrix multiplication on the inputs array and the transposed weight array W. Then adds the transposed bias B. The result is stored in the attribute Z, and we then apply the activation function to Z and then store in A, returning this as the layer's output. It's worth noting that while the code differs slightly from the single neuron example shown earlier, the math is the same for each individual neuron and sample, just generalized for the entire layer and all input samples at once. Comment beside each line note the dimension of the arrays to help clarify what's happening in each calculation. Next, let's implement the updateWeights method to adjust the weights and biases. This method takes three inputs: delta, the error calculated during backpropagation, activations, the values input into the layer that caused the error, and LR, the learning rate. The delta and activation arrays represent all the errors and activation for each data sample in the batch, and the code updates the weights and biases accordingly. We also average the adjustment over the batch to create the more stable learning process, achieved by dividing by the batch size. The next step is to create neural network class and initialize it with a list of layer objects we have just defined. Next, we'll create the predict method, which accepts a set of input data. This method will loop over each layer sequentially, calling its forward method to pass the data through each layer of the network. The input to each layer will be the output from previous layer. The most important method in this class is fit, which contains the majority of the code responsible for training the network. Let's start by explaining the parameters. Inputs is a 2D array containing all the training data, with rows representing data samples and columns representing features. Outputs is a 1D array of target values, with each element representing the correct answer for a given input sample. Epochs is the number of training cycles the network will go through, iterating over entire dataset. LR is the learning rate, controlling the size of each weight update step. Batch size is the number of samples the network processes before updating the weights. Using batches can stabilize training by averaging the updates over multiple samples. To start, we initialize an empty list called epoch losses to store the MSE error for each epoch. Then we create two nested loops. The outer loop is for the epochs, going through the entire dataset each cycle. The inner loop divides the data into batches processed in groups of batch size samples. We use batch counter to keep track of batches and adjust the start and end indices accordingly. This allows us to slice the input and output arrays to create input batch and output batch. Note that for output batch, we use reshape to ensure it has an extra dimension compatible with other arrays in the calculation. Within each batch, the network makes prediction, storing the initial input data and each layer's output in the activation list for later use during backpropagation. Now that predictions are complete, we can start backpropagation. We begin with the output layer and compute its delta error, which will be propagated backwards through the network. We decompose the calculation into separate variables for clarity. The computed delta value is stored in a list, as we will need it later to update weights. In a loop, we calculate delta for each hidden layer, moving backwards from the penultimate layer to the first. Since the output layer's delta is already known, each subsequent delta is calculated using the error for the next layer weighted by connection to it. The next step uses matrix multiplication and inserts each calculated delta at the beginning of the list to keep layer ordering consistent. Here we calculate and store error for each batch. This batch loss will contribute to the average epoch loss, showing how the model performs on the entire dataset during training. With the calculated delta and activation for each layer, we can now update the weights and biases. This is done through the update weights method, which adjusts each layer's weights based on the corresponding delta and activation value. Here the LR parameter scales the updates according to the learning rate as discussed. After updating weights, we increment the batch counter and adjust the start and ending indices to move to the next batch within the epoch. This loop continues until all batches in the current epoch have been processed. At the end of each epoch, we compute the mean batch loss and add it to the epoch losses list. This list is returned at the end of the training, providing a record of how the network's error decreased over time. Having completed the code of our neural network model, it's time to test it in action. To do this, we will switch over a notebook environment where we can clearly observe the outputs step by step. Let's begin by importing NumPy and all the elements from the neural network code we have written so far. Next, we will use previously defined generate data function to generate 100 samples of training data. We will then split the dataset into training and test sets in a 80-20 ratio, as is commonly done with machine learning algorithms. With the data prepared, we can now instantiate our neural network using two-layer objects. Note that the number of neurons, units, in the first layer must match the input size of the next layer. For this example, we'll use rectified linear unit activation function in the first layer, while using the identity function in the final layer. This is because our problem, a linear equation, can take on both positive and negative values. To accommodate this, we use the identity activation in the output layer, as it can output values in the range from negative infinity to positive infinity. Finally, we train our model using the fit method with the training data. For this simple example, we don't need complex network. Ours will train over 15 epochs with the batch size of 8 and learning rate of 0.001. The training error for each epoch will be stored in the history variable. Now we can make prediction on the test set that the network has not seen before. We'll compare the predicted values from the predict method with the actual value and display the mean square error to assess accuracy. As you will see, even with a small dataset and limited epochs, the results are quite satisfactory. Finally, we will visualize the training history stored in history. By importing pyplot from matplotlib, we can easily plot the mean square error over each epoch, giving a clear picture of how the network's predictions improve as training process. This concludes our exploration of neural networks, covering both the theory and practical implementation. We covered a significant amount of material, from concepts like batches, backpropagation, and activation functions. We've now grasped the key components required to understand and create a neural network from scratch. We didn't delve into issues like overfitting or fine-tuning of hyperparameters, but this video aimed primarily to give a deeper understanding of how neural networks function at their core. I hope this tutorial has achieved that goal. That's all for today. Feel free to leave any question in the comments. If you found this content valuable and interesting, consider liking, sharing and subscribing. This will be a tremendous help for growth of this channel and great satisfaction for me as a creator. Thanks you for watching and see you in the next video.